We will pick back up with division algorithms where we left off last time. And the standard algorithm, I'll repeat that one since you guys said that I had done that one. And we will take a look at how we think about and process through 623 divided by 5. Okay, so what we really look at when we are doing this is we kind of go number by number, and we start with the 6, and we ask ourselves something like this. How many times will 5 go into 6? And the answer is 1. And then we say 1 times 5 is 5. We write it down and then we subtract, giving us a 1. And we know that that's an acceptable answer at this point because 1 doesn't go into 5 evenly, right? So then we can pull down the 2 like this. We've got a 12 now. So how many times will 5 go into 12? 2 times. 2 times 5 is 10. And we subtract, leaving us a 2. And we bring down our 3. 2, 3, 23. So how many times will 5 go into 23? 4 times. And 4 times 5 is 20, leaving us with 3. And at the age level when you're first learning multiplication, division kind of facts, the way that you always see this answer written is 124, 124. And you do an R, 3, for remainder 3, right? As you move into the upper elementary grades, lower middle school, you start using fractions to represent the end part of that. But at the beginning, you're looking at remainders only. So this is the standard algorithm. One of the things that's hidden in the side of the standard algorithm that you know, and you don't even think about it anymore, is you know your multiplication facts, don't you? You didn't have to sit there and try and really figure out how many 5s were in 12. You just know it. Agreed? So I worked with a 5th grade class at one point, and there were a couple of students in that classroom who were special needs students. And memorization was really hard for them. That was one of their issues, okay? And so they literally had a multiplication table taped to the top of their desk in 5th grade because they couldn't. I mean, it was truly a disability, all right? So this makes division really hard if you don't know your multiplication facts, right? Really does. Now, I want to show you the repeated subtraction algorithm because it has the appeal that it will work without those memorization of facts. The drawback is that it's more time consuming. Okay? So anytime we try to do something different, there's usually some kind of drawback somewhere. And that's the drawback for this one. So go ahead and write down 623 divided by 5, much like you did a minute ago. And what we're going to be doing is we're going to be repeatedly subtracting things. Now we did this in section 3.3 already. We talked about repeated subtraction, but we do not want to subtract 5 from this thing infinitely many times. I mean, it wouldn't be infinite, but you know what I'm saying. It would take a long time to subtract 5 from this and actually get 623 to turn into 3, wouldn't it? So what we're going to do is we're going to subtract multiples of 5, and we're doing multiples of base 10 of 5. So let me show you what I mean. We're going to subtract numbers like 5 and 50 and 500 and 5,000, basically 5s followed by zeros. Okay, so we're not subtracting 10 because 10 is not 5 with a 0 behind it. It's always going to be the number we're dividing by followed by zeros. So if I put a 5 and a 0 here, this is small enough that I can subtract. And if I used a 5 with 3 zeros, 5,000, it'd be too big. Are you with me? Like this is like the 3 bears. This is just the right size. All right, it's not too big, it's not too small, it's just the right size to subtract. Can't do anything any bigger, anything smaller is going to take a lot more time. So we're going to subtract, and what we actually did here is this is 5 times 100, agreed? That's what we're really subtracting. So I'm going to jot that down to the side. We subtract and we get 123. Okay, so that's all well and good. Also, it's nice because I'm subtracting with zeros. Subtracting with lots of zeros is also friendly. I can't subtract 500 again, right? If I could, I would do that, but I can't. So now I need a 5 followed by how many zeros? 1, because that's all I have that I'm able to subtract. It's just the right size. So 5 times 10 is what I really just did. And when I subtract 123 minus 50, what do we get? 73. Can I subtract 50 again? Yes, so I'm going to. So I subtracted another 5 times 10. That leaves me with 23. Can I subtract 50 again? No. So now what am I going to have to subtract? Just 5. That's all I have left. And 5 is the same as 5 times 1. I know that sounds a little bit silly, but you'll see why I wrote it down in a minute. We subtract 23 minus 5, and what do we get? 18. Can I subtract 5 again? Yes. So another 5 times 1, leaving me with 13. Can I subtract 5 again? Okay, it's another 5 times 1, leaving me with 8. Can I subtract 5 again? Yes, and that leaves me with 3, and that's too small. I'm almost out of space, but you guys have it written down, I'm sure correctly. Okay, so this is like what you would actually write down. This is the real written down part. The answer to the question is here. There is 124. And the remainder at the end is still that 3 that I had left over at the bottom. Again, you're probably thinking the drawbacks to this are pretty great, and they are if you have lots of numbers in them. If I had 999, we would be subtracting all day, right? If that were the answer, because we would have had to subtract 9 times and then 9 times again on something else, and then 9, that would be tedious. But the benefit is that you did not rely upon any fact of multiplication that you knew, aside from the fact that I had a 5 followed by zeros, right? So that's the appeal. All right, any questions on this one? Okay, what we're moving into next is we're going to do some application problems. We haven't done a lot of application problems like these since the problem solving section, chapter 1. So as we work through these problems, they're going to feel like some of the things we did in section 1, but at the points when we're going to do multiplication or division, we might in fact decide we're not going to do the standard algorithm because we're going to practice the algorithms that we've been learning. Okay? So let's read through this one together. I don't know how to say his name, do you? Juan? Okay. Juan saved $5,340 in 3 years. If he saved $95 per month the first year and a fixed amount per month the last 2 years, how much did he save per month during the last 2 years? So this is like a multi-step problem. You can't just directly say, oh, I just need to multiply these 2 numbers and I'm done. There's more to it than that. So what do you think you might want to do first as you're setting up or solving this problem? What factor are we going to have to figure out? Subtract what? Not quite. Read carefully again. What was it, 95 per month for the first year?
So 95 times 12.
So that's what we'll do first before we do your subtraction. Okay, so the first thing we need is we need to figure out what is 95 times 12. All right, I'm going to avoid doing standard algorithms on pretty much all these problems because you know how to do those. That's not my point in this section. So would you like to do the lattice method right now, or would you like to do partial products? Lattice. Lattice it is. Okay, so lattice, you have to put the numbers on the top and on the left, I'm sorry, the right. Let me get the right values there. You make a grid. And since it's a 2 by 2, you need a 2 by 2 grid. You split along the diagonals, like so. And we're going to multiply each of the row and column combinations. So the top one is a 9, and it's on row 1, so 9 times 1 is 9, and we put it in the lower right-hand box. 5 times 1 is 5, lower right-hand box. 9 times 2 is 18, so we've got a 1 on the top and an 8 on the bottom. And then 5 times 2 is 10, so 1 on the top, 0 on the bottom. What's next in this process?
Extend the lattice.
Yeah, we're going to extend the lattice and we're going to add along the diagonals, right? All right, so on the bottom right, that's a 0. My next diagonal up is an 8 plus a 1 plus a 5. 14, so I'm going to put down a 4 and I'm going to carry the 1. 1 plus 9 plus 1 is 11. You can write down the 1 and carry it. If you just write down 11, it's okay because there's nothing in the next column to carry it to, so that would be okay. Your answer ends up being 1140. Now, what did we just find? We found how much money he saved in total the first year, correct? Okay, and then Rebecca, what did you want to do with that number? We want to subtract that number from the total amount that he saved during the 3 years, which was 5340 minus 1140, which is nice because there's no borrowing or anything in that one, right? Very straightforward subtraction. What do we end up with? 4,200. Okay, so 4,200 represents what? What is that? How much money total he saved the next 2 years? Okay? And the question actually asks us, how much money did he save per month during the last 2 years? And divide it by 24, because there's 24 months in a 2-year time span. So what I really need to do is I need to do 4,200 divided by 24. But again, you know how to do the standard algorithm. So what we're going to take a look at instead is doing the repeated subtraction. Let me also make one mention too. When I did repeated subtraction over here, part of what you didn't like when you were doing it was probably the fact that you felt like, I know my multiplication facts for the number 5. But I contend that you probably don't know your multiplication facts at least entirely for 24. Agreed? And whenever you are using the standard algorithm for numbers that are larger, usually larger than 10, but sometimes larger than 12, depending on what you learned in school, you sometimes make errors in the middle of a multiplication or in the middle of a division problem with the multiplication that you thought you knew, right? Oh, I think it goes in 5 times and you find out, oh, that was not enough or it was too much and you have to re-guess. So there's a little bit of guessing involved when you're doing the standard algorithm with numbers that are divisors, with their large divisors. So there's also kind of that going on. So this is a nicer one to think about doing this for purposes in general as opposed to the purposes just for a child who doesn't know their multiplication facts for a single digit multiplication. So we have a 4,200 here. So again, our goal is to subtract 24s followed by zeros, and 2,400 works here. And because there's 2 zeros, this is 24 times 100, right? So what is 4,200 minus 2,400? 1,800. So can I subtract 2,400 again? No. So what would I subtract next? 240. And the 240 is 24 times 10 because there's only 1 0 there. So what is 1,800 minus 240? What was it? 1,560 sounds good. Do we subtract 240 again? Yes, we can. So what is, this is 24 times 10. What is 1,560 minus 240? 1,320. Shall I subtract 240 again?
Yes.
Indeed. So what is 1,320 minus 240? Is it 1080?
Yes.
Okay. That was 24 times 10. We'll do it again, 240. It is getting smaller, step by step. This is 840, yeah? You can do 240 again. Now we're expecting this to come out to be an even number, like no remainders, in order to make this work in the concept, like the conceptual part of this problem. So we'll see if that happens. 24 times 10. 840 minus 240 is 600. Again, another 240. What's that? 360. Ooh, there's one more 240. You're about to hate me. Because now we're at 120. We got a 24. And when we subtract the 24, I'm sloppy because I'm running out of space. What do we get here? Yep, 96. Okay. So see, I can just, shrink things. It's a fantastic feature of an iPad. Okay, 96. Can I subtract 24 again?
Yes.
Or I'm sorry, Can't subtract 240 again, I should say, but I can subtract the 24 like I just did. I wrote it down wrong. This is 24 times 1 down here. Okay, so I can subtract 24 again, which is good. We're getting closer. That's 72. 24 again? Yes, that's giving me a 48. 24 again. Gives me 24. Lo and behold, we eventually end up with 0. And the crowd went wild. Okay, so let's see. How many hundreds do we have? 100. How many tens? 7 is what I'm counting as well. So far I have 170. And how many ones? 5. So this is 175. That would be our solution. And it was tedious because there were 7 of them and there were 5 of them following that, so we had lots and lots and lots of steps. If the numbers were smaller when we were doing the division, it wouldn't have been quite so tedious, obviously. Any questions about either of those processes, the lattice multiplication or repeated subtraction? Okay, let's take a look at another one. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as in the third box, and there are twice as many pennies in the second box as the first box. How much money does he have in each box? Okay, so you should tell Dan to take all of his coins to the credit union and turn them into dollar bills, and then we don't have to worry about it, right? That's what he should do. But that's not the problem. So, what are we going to do? When you hear or see or read this problem, what are your first thoughts? What did you think, Vanessa? There's some multiplication involved. Good. What else? Huh? There's some division involved, probably so, when we solve this, yeah. How are we going to start the problem? What are we going to do?
I just figure out which one has the least. Because like the third one's going to have the least, and if there's twice as, or no, 3 times as many pennies in the first box as in the third box, and you just like take that and multiply by 3.
Okay, so if we could figure out the smallest box, we should be able to find the other 2 boxes. I agree with that. But how are we going to go about doing that part, Rebecca? How are we going to find out the number in the smallest box? You could. That's one of our problem-solving strategies.
Like if you split it up into like all of the same amount in like 4 boxes, you'd know how many of that, and then you could divide the big number by however many.
Okay, so how many boxes would you have to do if you were doing that? Any ideas?
6.
I think you need more. Oh, wait, maybe you don't. Hang on. What did I read? I'm sorry, I may have read it wrong.
Sorry.
No, 6 might do it. What were you thinking, Catherine?
I was thinking about setting up more of a algebraic equation where n represented how many were in the third box, because that one is the smallest.
Okay.
And then multiplying by n to represent the other 2 boxes and make it equal to 45, 120.
Okay.
And it's all for n.
Okay, so let's go with some of the things that you guys are thinking about and combine a little bit of both of those ideas. Okay, so one of the things Rebecca said is that we've got a bunch of boxes, right? And if we could figure out how many is in the smallest box, we could multiply it by 2 and then multiply that by 3, or vice versa, or whatever we've got going on, right? And we could figure out how many are in each box that we're looking for. So I would contend that it might be helpful to sort of draw some sort of an image of where the boxes are to make sense about diagram-wise what's going on. Is that okay to you? All right, so I'm going to draw 3 boxes. Okay, and there's boxes, and I mean, he numbers them, so here's box 1, box 2, and box 3. And from the description that he says, which box has the smallest? Was it the third box? I think that's right. Yeah, that's how I'm reading it as well. He says there are 3 times as many pennies in the first as the third, and twice as many in the second as the first. So this one has some number of pennies, x, like, or n, like you were saying, Catherine, right? That's what we don't know. And then we can actually say that there is what you were thinking, like if you have 3x or x plus x, basically, for the first box. So here's 3x. And then how many are going to be in box 2? That'd be 6x. So why is it 6x and not 2x?
It's 2 times.
twice the first box. So if you were thinking about splitting it up into boxes, this actually looks like you'd need 10 boxes, doesn't it? Right? 6, 7, 8, 9, then we'd have to have 10 to actually make it equal. Yeah? Okay, cool. All right, so we have 3x, 6x, and x, and what are we going to do with all these quantities now?
We're going to add them together and set them equal to 4,520 pennies, right?
So there's 4,520 pennies total in all of these boxes. So if I add the contents of each box, whether I've split it apart into the 3 boxes like we actually are describing, or into 10 boxes so that they're all exactly equal, I still have 10 equal quantities, okay, eventually when I combine them. Because 6x plus 3x plus x is in fact 10x. So we get to the same point right here either way. And then what would I need to do to solve for x? I would need to divide by 10. Now, we won't belabor the point too much, but we should probably recognize at this point that when we're dividing by 10, 10 has a really nice feature that no other number does. Well, I shouldn't say no other number, but powers of 10, is that if it ends in a 0, then you're able to actually cancel out zeros like this, right? You can't do that with other numbers. Like if this ended in a 9 on the top and the bottom, you just can't cancel the 9s. Yes? You can't do that. I had somebody do that on a paper in this class one semester for me. You can't do that with any other number. It only works with zeros. Okay, so there's not anything mysterious about it. It's just that that's what the fact is when you divide by 0, is it cancels out the last 0. So that's kind of cool. I ended up with x on the left and ended up with 452 on the right. So this actually tells me that I have 452 what? Pennies in the third box. So let's see if we can figure out what's in the other boxes. So this is actually 452 pennies. How am I going to figure out one of the other boxes? I would multiply. So 3 times the 452 would give me box number 1. All right, so just for fun, let's actually do that. I'll write it that way. How can I do that with some other multiplication fact method than the standard algorithm? Partial products, let's do that one. We haven't done that one yet. Okay, so with partial products, I can do a 3 by 2 box. I didn't write that right. Let me try that again. 452, that's what I wanted. And I can split the boxes like this. You can move left to right or right to left, doesn't matter, but what is 400 times 3? 1,200. What is 50 times 3? 150. And 2 times 3? 6. And then I can add 1,200 plus 150 plus 6 together to give me a grand total of 1356. So in box number 1, there's 1356. Now you have at least 2 different ways to do box number, no, I can think of 3 different ways to do box number 2. So somebody tell me one thing.
Multiply box 1 by 2.
Okay, so you could take box number 1, which was 1356, and you could double it. Right? Because box 2 is double box 1. Tell me another way. You can multiply the 452. We can multiply box 3 by 6. And there is at least one other way.
Add the 2 values that you know and subtract it from 450.
Right. There's got to be a total of 4,520 right, pennies in all 3 boxes. So we can subtract off the 452 and the 1356 from that, and we can find out our missing box. Any of those ways are perfectly fine. Probably the multiply by 2 is our quickest one. So let's do that one. So if we take our 1356 and we multiply by 2, we'll use the standard algorithm here since I haven't done that one yet. So I would do 2 times 6, which is 12. I'd write down a 2 and I'd carry a 1. And what you heard me say in the video is the reason that looks and feels weird is because you're doing carrying in the middle of a multiplication and you're about to do an addition in the middle of multiplication as well, which makes it a little messy. 2 times 5 is 10, and then I add a 1. Like, that's a little weird. So we'll write down a 1 and we'll carry a 1 for 11. 2 times 3 is 6, plus 1 is, and then 2 times 1 is 2. So it's 27, 12. Now, did we answer the question?
Yes. How much money is
What did we do, Jessica?
Maybe we counted just the penny.
We counted how many pennies he has,
Not the amount.
but not the amount. So what do you think it's really asking me to find? Put it in dollars, because that's how we represent money, right? Our money is always represented in dollars. Even when we have coins, we represent 25 cents as 0.25 with a dollar sign. Agreed? That's how we usually represent it on the shelves. We don't usually see cents actually even marked, even when it is cents. So if we're actually giving the answer here, then, well, I'll just write it down here in the middle. So box 1 has what? So what? $13, right? Don't make it too hard. $13.56. Box 2 has what? $27.12. And box 3 has $4.52. So make sure, just like when we were doing problem solving in chapter 1, that you really do look carefully at what question was asked so you're answering the real question they were asking you. Okay, let's take a look at example 9. A student observes that 39 plus 41 is the same as 40 plus 40 and asks if 39 times 41 is equal to 40 times 40. How do you respond?
With the addition, it's more of like the values are kind of being rearranged a little bit so it's easier to work with. You still got the same amount of whatever it is you're adding together. You're just kind of moving it around a little bit. I don't think that works the same with multiplication.
Okay, so Catherine says she doesn't think that that will work for multiplication. Do you guys agree with her? Yeah. So how are we going to justify to the child who asked this that we don't think this is going to work? A counterexample. And do we even have to really come up with a counterexample?
No, you just do
We can use the one they gave us even, right? They didn't ask it kind of in general. They asked for a specific example if it worked. So real quick, we can actually answer the question. So we can check it out with the child. We can say, well, let's try, right? What is 39 times 41? And what is 40 times 40? What are the answers to those questions? So without giving too much of what's going on, let's just answer that. I'm not even caring that we multiply it out by hand necessarily. We're looking more conceptual at this particular problem. What is 39 times 41? You can grab your calculator if you'd like.
1,599.
All right. And what is 40 times 40? Yep, 1,600 or 1,600. So the real direct answer to the student's question is no. It isn't true. All right? Now they might want to know why. That's not what this particular question asked. But I think that that's similar to what we're going to be asked on number 10. Okay, so the answer here is that no, it does not work. And I'm going to sort of delve away, and we can show with an example that it doesn't work. But I want to show you a little bit more on the why as we look at problem 10 anyway, so we'll just put a hold on this particular problem and look at the next one. Because it's the same idea. We've got that same 39 times 41. So another student observes that 39 times 41 is the same as 40 times 40 minus 1. Now, is that true?
Yes.
Yeah, it's just one less. Agreed? And if you really were working this problem out by hand as opposed to your calculator, which of these two is easier to calculate? 40 times 40, like by a lot, right? I don't care which method we use of all our methods we have, it's way easier to calculate 40 times 40. So if what the student is observing actually holds in a general way, this would be useful information. He finds also that if you do this with 49 times 51, you also get that that's 50 times 50 minus 1. So he wants to know if the pattern continues. And if it does, what does the relation have to be between the first two values in the equation? In other words, how do these numbers have to be related to one another for this to actually work? So we need to figure out if this always works. Okay, so let's actually look at the relationship that he has asked about as it's stated. How are 39 and 41 and 49 and 51 related to each other individually? How do they compare?
One number is too less than the other number.
Yes. Whatever one number is, the other one's either too bigger or too smaller, depending on which one you looked at first, correct? So basically, you've got two numbers that differ by 2. One of them is too bigger than the other one. So if we're actually answering his question, that's probably the relationship that he's talking about, right? Will this always happen? If I choose two numbers like this, will it always happen? And maybe also, do they even have to be like with a value with a 0 in between them? Right? Like 39 and 41 had 40, which is super nice and friendly between them, but does it have to be that way? For example, would 34 and 32 work? They differ by 2. 33 is in between them. It's not necessarily a pretty number, but would it still work? Okay, so let's actually take a look, and I'm going to show you how to think about a problem when you're actually asked to find something as an in general case. Okay, so this is not something that you would show to the child, what I'm about to show you, but it is something that you guys have the mathematical maturity to be able to do with the math you've had. So Catherine commented and said one of them was too bigger or too smaller than the other one. And you guys all shook your head and said, yeah, everybody's good with that, right? So if we think about that in terms of algebra, and we let one of the values be x, then the other one is x plus 2. Does everybody agree with that? So whatever one of the numbers is, the other one's too bigger. So let's think about in terms of algebra, what happens when you multiply x times x plus 2? What do you get? X squared plus 2x. Fantastic. Everybody good so far? Okay, so this is like the left-hand side of these equations. The two numbers that are separated by 2 multiplied together. What I want us to do then is to look at the right-hand sides of the equation. How does the first number, 40 times 40, or 50 times 50, compare to the other numbers on the other side of the equation?
It's the number that's in between.
It's the number that's in between, right? Yeah. So in particular, if the number before was x and the number afterwards is x plus 2, what's the number in the middle? X plus 1, right? Because it goes x plus 1, x plus 2. X plus 1 would be in the middle. So on the right-hand side, what we have is we have x plus 1 times x plus 1, and then minus 1, because that's the relationship that he's noticing with the minus 1 on the end. So it's the number in between times itself, and then minus 1. Now, I actually watched two student teachers. Actually, I watched 3 student teachers yesterday, but I watched one of my 3 student teachers teach an algebra class where he was doing this in their class yesterday. Do you remember what you called it when you multiplied x plus 1 times x plus 1? There's more than one option here, by the way. FOIL? Or did anybody else have a different word they used? So the general word for it is distribution. Okay, what you're doing is distribution. Foiling is a specific acronym that we like to use because it's got some beautiful connotations with it. I actually showed the student teacher, afterwards too, another way that I have seen used before that he didn't use. So I'll show you it as well, just because it's kind of fun. So I had a student teacher I observed a couple years ago, and she had a student teacher or a cooperating teacher who drew this because it looks like a face. How cute is that, right? A nice visual connotation for that. So however you like to do it, we're going to FOIL. We're going to distribute out the result here. So I have one of my 2 facts here, which is x times x, which gives me what? X squared. The outer, or the bottom part of my face, is x times 1, which gives me x. The inner is 1 times x, which gives me, oh, I didn't draw that right. There it goes. Which gives me x. And then the last terms, which is 1 plus 1 times 1, which gives me 1. And I have the minus 1 on the end coming down from above. So x squared is good. These terms are like terms. X plus x is 2x. And then beautifully noticed here at the end, I've got a plus 1 and a minus 1, and they cancel out or add to 0. And what do you notice that your result was when you did this? They're the same. So what this actually shows is it shows that the two numbers could be any two numbers that are 2 apart. They were specifically 2 apart because we had x and x plus 2. So that couldn't be like 4 apart and 1 and halfway in between. That was not the generalization that we created. They were 2 apart with 1 in between. All right, so this will always work. And the realization is it will work as long as, or only if, or whatever language you like, the numbers differ by 2. You can say the original numbers differ by 2.